Thank you, and thank you to the organizers, Gilliam and Max, for inviting me and giving me a chance to speak here at HOPE. So I'll be talking about some work that's I've been working on for multiple years. It's called synthetic guided domain theory. And sort of the very brief idea of what I'm going to say here is I'm going to present a type theory with guided recursion, and I'll show how to use that as a meta-language for constructing denotational and operational semantics and relating the two within the same type theory. So, to motivate that and sort of to get started, I want to talk about meta-languages for semantics in general, sort of where do we do, and settings for doing semantics, right? And sort of the traditional meta-language for doing semantics is set theory, and that's, so if you open a book on this, you know, this is it's usually presented as set, so you can, and you can even use set theory as a model of many programming languages, including the simply type lambda calculus. And it's a very simple model. So types are just sets, and terms are just functions between sets. You know, and then you can go a little bit further, and you can add effects using monads, but it's still a very simple model. So the problem here arises when you want to do recursion. And of course, we want to do recursion in many programming languages. And I think the leading mathematical theory of recursion, still to this day probably, is domain theory. And in domain theory, the model becomes a bit more complicated. So now types are no longer just sets, but they're domains, so some kind of ordered sets. And functions are not just, or terms are not just functions, but they're monotone and continuous functions. And so as you go along and you define your, in particular, the denotational semantics, then you need to ensure as you go along that everything is continuous, because otherwise the constructions will break down. So that's a bit of an overhead. Of course, there are ways of handling this, and one way would be to have a meta-language for domain theory. People have done this, in particular using linear types. So then, if you have, you can use a linear lambda calculus, and then everything that you write in this linear lambda calculus can then be interpreted into domain theory, and is automatically then continuous, right? And sort of that's what I mean by meta-language. Okay, and so when I talk about recursion, I don't just mean recursive terms, but also recursive types. You know, and domain theory has been successful with this, in particular solving domain equations like this one here for the untyped lambda calculus, or variants of this. But the domain theory is sort of has more problems handling equations like this, domain equations like this, which arise when you want to model advanced features like higher order store, so the ability to store programs also of higher order in memory. And in fact, you cannot solve this equation here, so I'm not going to spell out what it is, but you can't solve this equation here exactly because of the lack of continuity. Okay, so let's look at a different way of modeling recursion. And here's a monad for recursion. And I think Venancio Capretta was the first one to study this. It's called the delay monad, and it's the co-inductive solution to this type equation up here. Right? So it says essentially in this monad, a computation is either a value of type A, or it's a computation that can run for at least one more step. So, so then you could be twice on this side and then here, and that would be a computation that takes 2 steps and then returns a value. Or you could be infinitely often here, and that would be a diverging computation. And so Capretta suggested this as a model of recursion in type theory, and it has indeed been used like this way, and it forms, I think, part of the foundation of interaction trees, which are also a successful way of modeling programming languages with many features here. The one thing here is that it counts steps, so it's intentional compared to the domain theoretic semantics that I was talking about before. Okay, and so I want to think of this as a monad for recursion. But is it really a monad for the recursion? I mean, what kind of recursion am I talking about? Well, you can do an iteration operator of this type here, right? So if you get a function like this, you know, you feed in an A. If it returns a B, then you immediately return that. If it returns an A, then you call yourself. So you can do sort of this kind of iteration. But there's no fixed point operator of this type here, right? And this is what you would need to model, general fixed points in higher order programming languages. And in fact, Venancio Capretta introduced the notion of continuity in his paper, which allowed you then to take fixed points of continuous maps. Okay, but then we're back sort of at the domain theoretic setting. So guarded recursion allows us to change the delay modality slightly by introducing a modal operator here, which corresponds to a time step on a clock kappa. And then once we do that, we can use this modality later here to ensure that all programs, or everything we write in this meta-language, in this language here, is continuous. Okay, and the way we do that is we have a fixed point operator which has this type here. So it takes a delayed input, it takes a function that takes a delayed input and returns an output now, and then returns a fixed point for it. And if we use this, then we can actually type a fixed point combinator like this. So for all functions, no continuity restrictions. And we can even, so this is a special kind of, it's called a guarded recursive type. And we can even go back to the co-inductive one by quantifying over the clocks. And this is, that's why I've quantified, that's why I have indexed these by clocks. If you quantify here, you get the co-inductive solution to the equation I was talking about before. So we can go back to the other viewpoint when we need that. Okay, so this is very briefly what guarded recursion is about. And so here's an okay, I forgot this one. So we can also solve more general recursive type equations like this one here, as long as we put a later outside of the equation here. So we guard sort of the recursive occurrence of t here by a later modality somewhere. And we can solve these kind of equations, and we can also build models of programming languages with high order store. I'm not going to talk about that today. So, but here's an overview of what I am going to talk about today. And I'll start by giving sort of an introduction to guarded recursion and presenting the type theory that I'm working in. It's called clock cubical type theory. And I won't assume that you know anything about cubical type theory, but I actually don't use much of that at all in this talk. And then I'll show how to construct operational semantics, denotational semantics, and prove an adequacy theorem between the two, all inside of this type theory. And I'll do it first for FPC, which is the simply type lambda calculus, extended with recursive types. And then I'll do it for FPC extended with probabilistic choice. And there's an issue here of working up to weak bisimilarity, the thing we were talking about, I was mentioning before, that we count the steps. We want to equate things that are weakly bisimilar, so compute the same thing up to just a finite number of steps. Okay, and so I'll do this first for FPC, and then I'll do it for this one here. And in the end, there will be a few examples of reasoning using our results for probabilistic programs. Okay, so since I'm giving an overview of this, I thought I should also give an overview of the literature. And to me, this work started with Marco Paviotti's PhD thesis. In 2016, there were 2 papers on this. And you might say, well, this one here was also at LIX in 2016. This one here does denotational semantics of FPC, so you might say the whole first part of the talk is just about this. Right? But I will present it in a slightly different way than it's presented in this paper. Instead, I'll actually be presenting the results of this recent preprint here. And the methods we will do, in particular for handling weak bisimilarity, will be different than what we did in Marco Paviotti's PhD. I should also mention that there's a series of works from the Aarhus group, and in this group they extend to languages also that have higher order store, which I won't be talking about today. Okay. So let me start by presenting the language, the meta-language guard type theory with guarded recursion that I'll be working in. And the precise language that I'll be using is called clock cubical type theory. It's an extension of cubical type theory. But I will not be using anything cubical. As I said, I won't be assuming that you know cubical type theory already. In particular, I will not be using any higher structure. All interpretations of types, for instance, will be sets or homotopy sets. And I will not be using univalence at all. One thing I will be using is higher inductive types, and I'll be using these to represent finite distributions. So that's a small thing. You can even think of this as a quotient type that sort of appears by magic. The reason why this is all tied up to cubical type theory is that cubical is an extensional, well, it's a type theory that allows many extensional principles to compute, including some that we need in this one here. And this means that it's actually been implemented in a version of cubical ACTA. So you could, in principle, you could implement anything that I talk about here in cubical ACTA, but we haven't done that. So to those of you who know cubical type theory, when I say set, I mean H set, and when I say prop, I mean H propositions. Okay, so here's guarded recursion. So I'll be working in a type theory with guarded recursion, and this means that I will have a modal operator later here, which is indexed by a clock, and you can put assumptions like kappa is a clock, you can put that in the context, and that's the only way of introducing clocks. And then I have recursive types, guarded recursive types, and these are recursive types where the recursive type, recursive variable here only occurs underneath a later here. And so there's this type, this example of the guarded delay monad, and I'm just naming the two inclusions here like this, like step and now, and anything in this it turns out to be a monad, anything in this type here is either of the form now or of the form step. And then there's a fixed point operator, which takes a function of this type here, and so in order to say that it produces a fixed point, well, you need this next operation here, which takes data now into data one time step from now. So you can think of this as this type here as data delayed by one time step on clock kappa. So it transports data into the future, and then you can say that the fixed point here is a fixed point. Fixed point of f is a fixed point of f composed with next. And now the fixed point equation types. So for instance, you can take the fixed point of the step function up here, and that would be the diverging computation. And when you instantiate this equation here, you get that bottom equal to step of bottom, essentially. Okay, and so I'll be presenting the language here for reasoning. I think it's nice to also be familiar, for intuitions at least, with the standard model, which is the topos of trees. Okay, so I'll just present that very briefly. I think it's helpful to have these intuitions of what in particular what later means. So the topos of trees, in the topos of trees, a type is modeled, or a closed type at least is modeled as a family of sets with maps between them, so natural number index family of sets. And you can think of x of 2 as the type as it looks if you have 2 steps to reason about it. And then the delay here shifts the sequence to the right and introduces a singleton here. You have 2 steps to reason about delay of x. Well, you need 1 step to unpack the x, and then you have 1 step left to reason about the x. And so in particular, if we look at the solution to this recursive type equation, well, it's this type here. So you have 3 versions of the natural numbers plus 1. You can think of this as saying, well, you have a natural number. You can either have a natural number now, a natural number that's computed in 1 step, or one that's computed in 2 steps, or you can diverge. And if you take this object here and apply later to it and then add the natural numbers, you get this thing down here, which is, I hope, obviously isomorphic to that thing up here. So it's an example of how we solve recursive domain equations in this model. Okay, this is topos of trees. It doesn't account for the multiple clocks, but it gives the intuition. So here, is a graphical representation, you might say, of this object here. So here I have my 3 copies of natural numbers and my point of divergence in here. And in this model, closed terms are modeled as global elements of this one here. So you can have a natural number now, then that would be picking this one up down here. So picking the same number in all of these copies of n. Or you can have a natural number after 2 steps, and then that would be picking divergence here, divergence. And then natural numbers here, picking the number that you're returning here. Or you can have divergence, which is like this element up here. And indeed, you know, if you take the limit of this construction here, you get the usual co-inductive version of the co-inductive solution to the delay or the co-inductive delay monad. And taking limits corresponds to quantifying over clocks. So that's what we do here. So when you quantify over the clocks, I'll call it L for all A. I quantify over the clock that's used in this guided recursive type, and then I get a co-inductive solution to this thing here. I call it the Atkin-McBride encoding. It's a technical requirement here on A, which is always satisfied in practice. I won't get into this. Okay, but this allows us to pass from the guided recursive viewpoint to the co-inductive one, and actually using guided recursion to program with co-inductive types, which I think is very useful. Okay, and then the main thing you need to know in order to understand the programs that I will write is sort of the tick calculus or the fit style programming that we'll be using for programming with this delay, with this modal type here. Right? And so, so we use a notion of ticks, and so you can put a tick and a tick assumption in the context, and this says alpha is a tick on clock kappa, so it's an evidence that time has passed on clock kappa. And then introduction into the later type here is just by abstracting ticks, and elimination is application to ticks. So the way you should read these typing rules is that everything that happens to the right of a tick happens one time step later than anything that's on the left. Okay? So this one here, for instance, says if T has type A one step after gamma, then at the time of gamma, this lambda abstraction here has type later A. Okay? But here the alpha, you know, this is like a pi type actually. The alpha can appear in A, so that's why I mentioned it here. And then the application here says if T has a later type at time gamma, then at this time here, since beta has happened, well, one time step has passed, we can open T to get the thing out that's using beta, the thing out of type A that T is supposed to deliver after one time step. Okay, and this is a very flexible way of programming with modalities in independent type theory. For instance, it allows us to write the thing I called next before is just an abstraction over a fresh tick here, or you can write an applicative function, function application here, also for dependent functions. So if I take a dependent function from A to B, I take a delayed input, then I can produce an output like this. Well, what do? Well, I open F with the tick alpha here, and I open the input, and then I apply them to each other like this. I apply the F of alpha to Y of alpha. And this gives me something of this type here, and you see we can use the tick alpha here to talk about which component of B we end up in. Okay, and another place where this is used is to talk about is for the extensionality principle for later. So two elements of later types are equal if it's later true that the thing that they deliver in the next time step are equal. So we can use the tick here to talk about the thing that they deliver in the next time step. Okay, so let me give a short example of reasoning in this type theory before I move on and talk about semantics. And so here's a small theorem that you can prove in the type theory. And it says that this type up here, the guarded delay monad applied to A, that's the free delay algebra on a type A. Let's think of these as sets even, so 8 sets. So by delay algebra, I mean a set B together with a map from later of B to B. Okay? And then these two equations here says, well, they express freeness of this construction here. So this is also a delay algebra because there's a step function like this. And it expresses freeness of this one. It says, whenever you have a function from A to B, I can extend it to a function from L kappa A to B. So this is the extension property, which is a homomorphism of delay algebras, which just means that this equation is satisfied. And so we need to prove existence and uniqueness, and both of them are proved by guarded recursion. So existence here, if I want to construct this f bar here, I do it by guarded recursion. So I assume that I have something later, and then I need to construct something of this type here. And I'll call that capital F of G. And there are two possible things that can be in here. It's a now. If I have a now A, I just apply F to it, and that's the only thing I can do to satisfy this equation up here. If it's a step, then what I do is I open, I can apply this, I want to apply this psi here, and I can apply that to some delayed data here. And once I have this tick alpha in hand, I can open the G to get a function from L kappa A to B, and now I can apply it to A of alpha. A was also delayed data. Okay? And so this f here gives me a function from later of this type from this type here to the thing without the later, and then I can take the fixed point of it, and then that f bar will have this type. And if you unfold the fixed point equation, like I did down here, you will see that this f bar here satisfies this equation here, and that thing here is precisely the later kappa of f. Okay? And so I'll not do, for the rest of the talk, I'll not do explicit applications of fixed point operators here. I'll just write guarded recursive definitions like this. And so here's the proof of uniqueness. Suppose I have another function, g here, which satisfies the property that f bar is satisfied. I want to show that g is equal to f bar. And again, I do that by guarded recursion. So I assume that it's later true, and then I want to show that it's true now. So this is my assumption, the guarded recursive assumption. This guarded recursive assumption easily implies that for all data of later type, it's later true that g applied to the thing that A delivers is the same as f bar applied to the thing that A delivers. This follows straightforwardly from this one here. And then by the extensionality principle, we can show that lambda alpha of this thing here is equal to that thing here. And we can then use that to show that g applied to something of the form step. Well, that must satisfy this because of this equation up here. And that thing is by definition later of g. And now these two are equal, as I just proved here, using my guarded recursion assumption. And now that's equal to that thing here, as we saw before. So g and f bar equal on things of type step. And they also equal on things of the form now. Okay, so that's a small example of proving things by guarded recursion. Okay, so then let's look at modeling FPC. So the FPC, as I said, is just the extension of simply type lambda calculus with recursive types. So here's a grammar for types. Here's some typing rules, and all this should be familiar. Here's lambda abstraction. I call that lam to distinguish it from the metalanguage lambda. Here's an application, and here's fold, just to remind you, if you have something of the unfolded type here, of the unfolded type here, then we can apply a fold to it, and you get something of the recursive type. Or if you have something of recursive type, you can unfold it to something of the unfolded type. And just to say where I'm going now, where I want to go with the developments here in this talk. Let's recall contextual equivalence or contextual approximation, and I think so. You would usually say that n contextually refines m if for all context C that takes that closes C m and n to closed terms of type unit. If C of m terminates, then also C of n terminates. That's a standard definition of contextual approximation for FPC. And you can then symmetrize this to contextual equivalence. Okay, and it's well known that it's hard to reason about this because you need to reason about all context. And there are various ways of doing it, techniques have been developed, so operational techniques and bisimulation techniques. But one form of proof that I'll be talking about here is using a denotation in semantics. And so this would be using a computational adequacy theorem, which essentially says that the model is adequate for reasoning about contextual equivalence. So if two terms are equal in the model, then they're contextually equivalent. Right? And this is a classical theorem in domain theory, and I'll do a version of this for guarded domain theory. Okay, but as a first step, I need to define even the operational and denotational semantics. Okay, so here's the guarded delay monad again. We've seen that a few times. It's the solution to this equation here. And just to remind you that I'm calling this inclusion step and this inclusion now. There's also a co-inductive version here, which I get by just quantifying over the clock. That satisfies this equation here. And there's a step here without a later, and there's a now here. And I'm using for all here whenever I'm talking about the co-inductive one, and the clock kappa whenever I talk about the guarded one. So, okay, so I want to define an operational semantics, and there are various ways of doing that, big step, small step. The way I'll do it here, I want to use this monad here, this guarded delay monad, and the way I do it, well, is I define an evaluation function which takes a term and computes its normal form, or computes its value. And of course that needs to be a partial function, but I can use this delay modality here to talk about these partial functions. Okay, and so here's the definition. Since this is a monad, well, I'll be using that. So if I have a value, I just return that immediately. If I have a function application, well, I evaluate the function first. That should, when that returns, it gives me a value of function types, and these are necessarily lambdas. They're all lambdas, so a pattern match on that. Then I evaluate n, that gives me a value, and I substitute v into m prime, and I evaluate the result. But here's the crucial part where we need to use guarded recursion, because m prime with v substituted for x is not a subterm of m of n. So we need some reason why this is well defined. And it's well defined by guarded recursion, exactly because this is underneath a later. So I could actually define this eval kappa as a fixed point, or that's what I do, but I haven't written it out explicitly as using the fixed point operator. But this is well defined by guarded recursion exactly because we are under a later here. With fold, I just apply, once I evaluate m here, once I get the result out, I just put a fold in front of it. And with the unfold, I essentially just need to take a fold off once I get a value out. But I do delay this by a step, and this is just to make a few things more easy. But I don't need to do that here. But this step here is crucial for the well-definedness of this evaluation function. Okay, and so a small example of a program in FPC, it's well known that recursive types imply recursive terms, and there's a fixed point operator that you can define. I don't want to spell that out. Usually you would have that satisfy a fixed point equation, which in terms of, in the corporate value setting, as we're in here, would say that y(f) applied to a value is the same as f of y(f) applied to a value. So essentially that this one is equal to that thing here. That's not true here with the evaluation function, the way I've defined it here, because evaluating this requires unfolding fixed points and doing beta reductions. And that introduces in total 4 steps like this. Okay, so there's a 4-step difference between the two. Okay, and so I want to be able, I need to be able to peel off steps, and also in order to be able to talk about even predicates like this term evaluates to a value. And the natural place to do that is on the co-inductive co-inductive side. So I do this, I define this evaluation function here by abstracting the lambda. I can go into the co-inductive delay monad. And then I define a step reduction relation which takes 2 of these and, it's a relation between 2 of these. Okay, and it essentially just, it's inductively defined and it just peels up steps. So this is the crucial ones, but it's also reflective and transitive. And now you can show that this one here, that this thing here, step reduces to that thing because the difference between the two is just 4 steps. So I can peel off these 4 steps. Okay, and I can also use this stepping relation here to talk about termination. I can ask whether a term evaluation of something like this here would twiddle to now of a value, and that would be termination. So that's what I do on the next step here, on the next slide here. So here's my definition of contextual equivalence. It says n contextually refines m if for all context when I put c of m in that context, and then that terminates to a value, then also C of n must terminate to a value. Okay? So let's do the denotational semantics. And the denotational semantics are, I think most of these clauses are straightforward. Here's a Kleisli exponential. Right, so I just use the monad here to represent a recursion. And for recursive types, I need to introduce a delay like this in order for this to be well defined. Okay, so I can actually define this interpretation function as a fixed point formally, like I did before, but I haven't spelled that out. And in practice, I just get a recursive domain equation like this. So the difference between a recursive types and its unfolding is a later. And so I can do interpretation of terms, and interpretation of terms is just straightforward. This is just of application is just straightforward because I just use the monadic structure of this one here. For fold here, when I evaluate M here, M has the unfolded type here, I want to go into I want to end up in the recursive type here, so I need to add a later, and I do that by using this step, which introduces a later. For the opposite direction, the M here that I get has the recursive type, and that is later of the type that I want. But I can eat this later using this delay modality here, and do that using the step like here. Okay. And so recall the computational adequacy statement in domain theory. It says that if two terms are equal in the model, then they're contextually equivalent. The key step for proving this is to show that this key lemma here, that if the denotation of a term terminates in the model, then also the term terminates in the operational semantics. Okay, and the equivalent statement would be this one here. Here's the denotation in the model, and I've I've stepped to the co-inductive one by quantifying over clocks. If that swells to now, then also the evaluation of M must terminate like this. And the way such a thing would be proved would be to essentially generalize the statement by constructing a logical relation indexed by types. And then use standard results or standard constructions for this. So this is what I'll do as well. I'll construct a relation between semantics and syntax, and then use that to prove this adequacy statement. And so the key step in doing that is a lifting relation. It's a notion of lifting relations using the monad here. So if you give me a relation from A to B, I would like to lift it to a relation between this co-inductive delay monad applied to A and B. And it should be, well, the natural, I think, definition would be that if the left-hand side terminates, then also the right-hand side must terminate to something that's related to the thing that you get out of the left-hand side. Okay? And I suppose you could define it this way, but I'm not going to define it this way. I'm going to define sort of an asymmetric version of that thing up here, where I have the guarded recursive type on the left and the co-inductive on the right. And the reason is that I want to define the relation that I'll do on the next slide. I want to define that by guarded recursion, and I want to be able to do guarded recursion on the left-hand side, so I use the guarded recursive type. And now the definition is, it's this one. I would say it's straightforward. So if you have a value on the left, then y must also terminate to something that's related to it. That's essentially this thing up here. But if I have a step on the left, then I just do a guarded recursive step, and I assume that later true that the thing that x returns is related to y. So, so this is my lifting, and I can use that in the definition of the logical relations, and there are two logical relations that I want to define here. So there's one on values that takes denotation between denotations of the type and values of that type here, syntactic values. And then there's one on terms, which is between the denotation of the type of the well, where I've applied discarded delay monad here, and where I have the co-inductive one here. And I pass from this one to that one, so the two are defined by mutual induction and guarded recursion, but the relation from here to here is just the lifting that I was talking about on the previous slide. And many of the other cases are standard, for instance, to relate two functions here. Well, two functions are related if for all related input values, they return related output terms, like this. The case of the recursive type is perhaps non-standard. So here for recursive types, I essentially use guarded recursion. So I just use the version of this relation here at the unfolded type underneath a later. And again, this is well defined by guarded recursion. This is where, in domain theory, you would need to argue that this definition is continuous, so that this type actually exists. But here it's straightforward just by typing. Okay, so I've defined a denotational semantics using guarded recursion. I've defined an operational semantics using guarded recursion. And I've defined a relation between the two also using guarded recursion. And now I can prove sort of standard results here, which would be these variants here of standard results would say that any term is related to itself in this relation. And this means that if you take a term and it's related to the value of another term, then n contextually refines of n. So we can use this relation here between semantics and syntax to reason about this contextual approximation and equivalence. And so you get, for instance, the computational adequacy result here, which says that if the denotation of two terms are equal, then also they're also contextually equivalent. This is perhaps not that useful in itself because many terms differ here by, well, it is useful for many things, but this is even more useful. If you twiddle from one to another, then they're also contextually equivalent, and you can do that on the right-hand side as well. Okay, and so one thing you get out of this straightforwardly is that contextual equivalence contains beta equality, as we know, but this is one application of this technique. Okay, any questions so far? Okay, so I've done this for FPC, and then I'll move on to talk about probabilistic FPC. And so probabilistic FPC is just FPC extended with probabilistic choice. So I have all the typing rules I had before, but now I also have a choice operation here indexed by a p. And this choice here means do m with probability p, do n with probability n minus, or p minus 1 minus p. M with probability p, n with probability 1 minus p. Okay. And so I want to use these techniques that I just showed you for reasoning about probabilistic programs, and let me just show you the examples we've done up front, just to give you an idea of where I'm going. So here's the hesitant identity function, which can be defined as a fixed point as well, and I've just written it in line here. The hesitant identity takes an input, and with probability p, it returns its output immediately. With probability 1 minus p, it calls itself recursively. Okay? So you would expect in the limit this behaves like the identity function. And we can actually prove that these two are contextually equivalent. Or this other example here where you simulate, well, this one is perhaps a toy example, this one's perhaps more interesting. You simulate a fair coin using an unfair coin. So if you have an unfair coin, you can simulate a fair coin by flipping it twice. If you get different result, you pick the first one. If you get the same result, you repeat the experiment. And this is what it says. That's essentially what this program here does. It flips it twice. If they're equal, then then you call yourself another. Otherwise, you return the first one. And we also proved that this one is contextually equivalent to a fair choice operation. So fair coin. Another example we did is the lazy list here. Or the random walk. So you can imagine doing a random walk on a natural number, so you start somewhere, right? And then in each step you either move to the left with probability a half, or you move to the right with probability a half, right? And if you look at what you do in 2 steps, then you either go like this, so you take 2 steps to the right with probability a quarter, you take 2 steps to the left with probability a quarter, or you go back and forth like this with probability a half. Okay? And so these 2 programs here represents the two walks. So here's the one where you do 1 step at a time, and here I do 2 steps at a time. Probability a half, I stay put. With probability a quarter, I do 2 steps to the left. Okay, and we proved that these 2 programs, well, if you take this one here and then cut out every other step, then you get this one up to contextual equivalence. Okay, and that's perhaps interesting because it uses a recursive type. Okay, so these are the kind of things that one would like to reason about for probabilistic programs, the kind of equivalences you would expect. You know, and there have been various techniques that have already been developed to do this, both operational techniques and by simulation techniques. Now I'm doing it in my setting, and the hope is that I think that this way of reasoning is fairly simple, I hope. Okay, and so here's the contextual equivalence that I'll be talking about before I define it in details. So what I'll be talking about is, you still take 2 terms here, you put them in the same context, but then the thing you observe is the probability of termination in the limit. So you run them for infinite time and you observe, the probability that they terminate, and you say this one, n refines m if the probability that, in any context here, of returning is greater than this one here. Okay, so this is where I want to go. Okay, and so then the first problem here is that, well, I'm in type theory and I want to model probabilistic computation. And the standard model of this is using the distribution monad. And here's the standard definition of the distribution monad, the classical definition. I'd say it's a function from A into the unit interval, which has finite support and whose values sum to 1. Okay? And then if you want to define its functorial of its action, then, you know, if f is a function from A to B, mu is a distribution of A's and B is an element in capital B, well, the value of this thing here should be a real number, and what you look at all the A's that map to B and you sum up the probability of these. Okay? Okay, and so here's here's a problem. If you want to do this in domain theory, in type theory, this definition here requires decidability of equality. And that particular type, in particular, but also this one here, depending on your meta theory, but certainly this one will not have decidable equality. It amounts essentially to solving the halting problem. So I need to do something else, and luckily there are ways around this, and one is to use convex algebras. So a convex algebra is a set together with a choice operation here, which take a probability, 2 elements of A and returns an A here, and you write it like this, and well, if you read this one here, it says do mu with probability P, do nu with probability 1 minus P, just like I had in FPC. Okay, and so a convex algebra is one that has these operations and satisfy these equation idempotency. If I either do mu or mu, then that's the same as doing mu. If I do mu with probability P, nu with probability 1 minus P, then that's the same as doing nu with probability 1 minus P and mu with probability P, commutativity, and then associativity, and let's not spell that one out. But so it's a standard theorem in classical mathematics, or you can easily prove that the distribution monad that I showed you before is the free convex algebra on a set. Okay, that's not true here in the setting of type theory that I'm in, but I'll just take this one as my definition. And the way that I can encode it, because I'm an extension of cubicle, is as a higher inductive type, and so that's what I do. Yeah.
Sorry. If A has decidable equality,
yes.
can you prove yes that they're equivalent?
And we did actually. That's in
Okay.
in the preprint I mentioned. At least for hang on, no, we did it for finite. We did it for finite sets. Yeah. Okay, so that's probabilistic choice in itself. Let's combine this with guarded recursion, and what I do is I use this, what we do is we use this guarded recursive type here, which again is a recursive fixed point, or guarded fixed point. So this says essentially that the monad I'll be using here, an element in it is either well, it's a distribution of things that are either values now or they're computations that can run for one more step. And so in particular, you know, I have a Dirac unit for it, or I can introduce step here. I can do the step here by using a Dirac for the outer distribution here, and then the right inclusion. And there's also a probabilistic choice here just from the distribution monad here. Okay? And so that's a guarded recursive type. If I universally quantify over the clock kappa, then I get the co-inductive type. And this is the co-inductive solution to this type equation here. And again, I get introductions here. Well, here's a Dirac, and there's a step, and there's no later here. That's the sort of the benefit of the co-inductive one. And then there's this probabilistic choice operation again. And so I can do, before I do that, let's look at an example here. So here's a guarded geometric process. So the geometric process is you flip a coin and you count how many coin flips you do until you see heads the first time. And so, so to implement that in a functional program, you would need some state here, and I do that by keeping a natural number here that tells me how many coin flips I've done. And so I can define this geo kappa here by guarded recursion again. So it says for this n here with probability p, I return n immediately. With probability 1 minus p, I do another step, and then I update my state here to n plus 1. Okay, and I can close this by quantifying over clocks, and I get something in the co-inductive one. And if I unfold the equations, I get this here. Okay, but let's look at a graphical presentation of a geometric process here. So it says with probability p, I return 0, probability 1 minus p, I do a step, and then at that point here, with probability p, I return 1, probability 1 minus p, I move down here, and so on. Okay, so this is an example of an element in this monad that I've defined, combining probabilistic choice and recursion. And I want to be able to talk about probability of termination. This is the defining thing I need for, the thing I need for contextual equivalence and contextual approximation. Okay, and so in order to talk about probability of termination, I'll introduce first a notion of running a process for some steps, and then a notion of determining the probability of termination after n steps. Okay, so here's the notion of running a process, and it just goes from this co-inductive type to itself, and it essentially just removes one level of steps here. Okay, and so maybe it's better again to do the graphical presentation here. Here's the geometric process. If I run it for one step, then I'll remove this step down here, and so I'll return 0 with probability p, 1 with probability 1 minus p times p, and then this thing down here with probability 1 minus p. So that's precisely what it says here. Okay, and then I can run it for one more step, and then I also get the 2 up, and that's like this here. Okay, so that's a notion of running processes. And then I want to talk about the probability of immediate termination. And this one here just says a value terminates, a step does not terminate, terminates with probability 0. And then if you have distribution of function of things here, then you just do the weighted average here. And so I can talk about termination after n step. I run a process for n steps, and then I measure immediate termination. And this gives me an increasing sequence of rational numbers in the interval. And this is essentially my representation of the real interval, which is what we need to talk about sort of for limits here. Okay, but I can use this representation, and I can easily define sort of notions of comparison of inequality, which one being larger than another one in the limit. And so before I do that, so let's look at the operational semantics here. So the operational semantics is precisely like before, but I've changed the monad to this one here that also incorporates probabilistic choice. And then I have a case for the choice operation here where I just use the probabilistic choice in this monad up here. And then the co-inductive one here similarly uses the D for all. And so now I can actually define the contextual approximation. I take two things here, I put them in the same context, and I evaluate. And then I look at this thing here, which for every natural number gives me an element in the rational interval, and I ask whether in the limit that one is larger than that thing here. Okay, and that's my definition of contextual approximation. The denotational semantics is also essentially like before. I've changed the monad again here, and I've added the case of probabilistic choice, just using the probabilistic choice in this monad. One thing that's different, and this is where it gets a bit technical, and maybe I shouldn't spend too much time getting into the details here, is this lifting of relations from between A and B, of relation from A to B to a relation between computations. Okay? And so let me sketch this. So there's a notion of lifting of computations from types to distributions on those types, and that's a notion of coupling, and I'll be building on that. So I have this thing here if I have a distribution of A's and a distribution of B's, there's a notion of coupling which allows me to lift a relation R to distributions like this. In a more general, what I do is I look at this distribution monad which satisfies this equation here. This monad here, the guarded convex delay monad, we call it. An element in here is a distribution between things that are either A's or delayed computations. And so there are basically three cases. Either all of these in the distribution are A's, or they're all delayed computations, or there's some convex combination of the two. And then I can use that to define my lifting of relations by cases. And so that's what I do on the next slide here. So, either what I have on the left-hand side is just a distribution of values now. I have all the values in hand. Then the thing on the right-hand side must twiddle in the limit, that's what this thing here means, to a new prime, and such that there's a coupling between the two. Or if it's a distribution of delayed computations, well, then I need to run all these delayed computations with one step, and in the next step, what I get out must be related to new, and so I just essentially use guarded recursion here. And then there's a case where mu is a combination of the two, and I just, I require that mu also twiddles to a combination, and that you can do, for each one of them, you can do this relation up here. Okay, so this was very quickly. This is probably the main technical contribution of that paper. Okay, so I haven't told you what the twiddle relation is. Maybe I shouldn't spend too much time on this. It's the extension of the, so first you do, so here I had a twiddle in the limit, so it step reduces in the limit to new prime. I first extend the step reduction relation I had before, which just took off the steps in the natural way for probabilistic choices. And then I define this in the limit thing here, which says essentially that I can get, from new I can get arbitrarily close to new prime with some residual new double prime here. So you can think of this as being sort of, you choose new double prime here with probability epsilon, and probability 1 minus epsilon, you have new prime, right? For any epsilon. Okay, and I can do the lifting of logical relations, that's just as before, and I can prove the results of the fundamental lemma and the main theorem just as before. And then in the examples, we will use this relation here to reason about contextual approximation. And we did that for all these 3 examples here. Maybe I'll just briefly show you the case of the hesitant identity, to give you a taste of this. So the hesitant identity takes an x, returns x with property p, and and calls itself recursively with property 1 minus p. If I want to show that this thing contextually approximates the identity, it suffices to show that the denotation of the hesitant identity approximates this one here. And this just means to map related input to related output. So I assume 2 things are related here, and I need to show this thing here. Okay? And if I unfold the definition of the hesitant identity, well, the hesitant identity returns v with property p and calls itself with property 1 minus p. But this requires unfolding a fixed point, so there's a step here. And so this equation here reduces to a later of this thing here. And so this means that we can easily prove by guarded recursion, we can prove this, because if we assume later of this, then that implies actually this equation here, which is just that thing up here, and we're done. Okay? So we can use guarded recursion also to reason about these examples. Okay, so here are the conclusions. So I showed you a type theory with guarded recursion, and I'm proposing this as a metalanguage for doing operational denotational semantics. We did both operational denotational semantics here. We proved contextual adequacy, computational adequacy, also within this type theory. And we use this for reasoning about examples of probabilistic FPC. And and this also extends to higher order store and other languages beyond the reach of domain theory, but I haven't talked about this in this talk. Okay, yeah, thank you.
Thanks. So we have time for questions. Hi, thanks for the nice talk. I was going to ask you to say how this compares with step index models, but I think you've got a bullet point there. Could you say a bit more about that?
Right. So before this work, Alejandro and Lars, Alejandro is actually in here, maybe he left. Alejandro and Lars did also, so many of the examples here, they did, at least these 2, I think maybe also this one here. As I said, there are different techniques for doing this, right? So they built a step index model of probabilistic FPC and then did this using operational techniques, and that's directly step indexed. Right? So one of the points here is just to use guarded recursion as an abstraction over the step index, right? And I think that's very useful because it's well, I mean, you have the step index techniques, and then they're very good. But once you have this modality here, and you encapsulate it like this, you can see, it's an abstraction. It allows you to see the type system that's there, dependent types and everything else.
Hi, thank you for the talk. So when you presented the model for the FPC, I was curious, so now you're adding a later step each time you have a function application, basically. So any kind of function application. I was wondering, so you have this, could you somehow make a model that only adds a later step if you actually use a delayed type or a recursive type, and make it evident in the model that, well, that if you don't use that, then you don't have non-termination. So.
So we add a step when we do operational semantics. So here's a step for beta. I think you said for beta reduction of functions, right? So here's a
Yes,
step,
indeed.
right? But in the denotational semantics, we didn't do that.
Ah, okay, so it's only in operational semantics. Oh, I missed that.
This is one reason why it's just simpler to reason about the denotational semantics, because there are fewer steps.
So you might get more steps in the operational semantics than...
Yeah. I mean, but so this is something that, okay, it's quite interesting, and something we worked on for a while, because it sort of in our first attempt we had a sort of a one-to-one correspondence between the steps in the operational and denotational semantics, and that allowed us to prove some things very easily. But then using it, the reasoning would be cluttered because there would be so many laters everywhere. You'd have to do. You would have to argue about this. But then it turned out, when we've thought more about it, that you can sort of, you can put in unnecessary laters somewhere, and then you can prove that that's equivalent to the one where you don't have these. Right? So this is actually how it's constructed. We do first the operational denotation and semantics, where the steps are aligned, and then we sort of proved later that you can remove the steps from the denotation and semantics.
Okay, thank you.
So when you define the probability distribution as the free convex algebra with direct and distribution mixing, doesn't that make it quite difficult to work with uniform distribution on the 0-1 interval? So if I wanted to model a uniform distribution on the 0-1 interval, I would need to use a quite complicated guarded recursion, isn't it?
Okay, so this, if I didn't make that clear, these are finite distributions. So you talk about the uniform distribution on the unit interval.
On the 0-1 Q interval.
Yeah, so that's outside of this, yeah. I don't think there's a simple encoding. Is there a simple algebraic description? I mean, there's these, there's this work on metric space algebras for encoding these continuous distributions as well. But that's sort of outside of what I'm doing here.
Thanks.
Okay, thank you, Rasmus. And I have a lot of questions, but I'll keep it to one or two. So first of all, big question, I guess, about guarded domain theory is that, like you say, the main issue with guarded domain theory is sometimes we do want to work ignoring the steps and working up to weak bisimilarity and everything. And so the first thing I want to ask you is about this question we've had basically since the beginning of step index logical relations, which is that it seems like neither classical domain theory nor guarded domain theory step index logical relations is strictly better than the other, in that old domain theory is less flexible and it's less general in some ways, that we can't do higher order store, but we actually get out the thing we want, which is the exact solution. And guarded domain theory, it's very flexible. We can basically do anything we can think of, but we always have to deal with this presence of steps. So do you think there's any hope of some kind of reconciliation between these two, or is this a good summary of the situation we're at still?
I agree with the summary.
Okay.
and this is something that I have thought quite a lot about. So yeah. I mean, here we sort of avoid it. We're building this relation. I mean, we need these relations anyway. I don't think we could just use the equality in the model to reason about programs like these. Right? So in a sense, but it would be very nice if they were equal.
Okay. Yeah. And then something of a technical question about these two proofs, right? So a lot of them is the same. Right, between the FBC for just recursion and then the FPC now extended with the probabilistic choice. And vast majority of the proof is really exactly the same, right? So what I would want to know is if you've looked into how you could abstract over the difference between these two, which seems to be what exactly is this monad that you're doing, if you've been able to come up with a nice abstraction of that part, that you could prove a generic kind of version of this theorem.
That's right, yeah. So, right, yeah, I would expect that you could do this you could generalize from this convex, this distribution monad, which is a free convex algebra, to any kind of algebra, so algebraic monads. I would expect that, yes. We haven't done that yet. And the funny thing is, so this construction here is just a free combination of the two.
Right.
And that's all it does. I just put this one out here, and I could have any other. And there's sort of there appears to be no benefit of combining them in a more clever way.
Yeah. So it's basically just any kind of algebraic theory you could do it at that level of generality, maybe.
Well, I mean, I mean, for this kind of reasoning, there appears to be no benefit of that. I think, I suppose, there could be a situation where you would combine them in different ways, and then you get a different equation of theory out, and then that would simplify things. Right? But as you say, there's a limit to how far you can go, because the steps will always be there. Yeah. And you can't eliminate those. But I'm working with, I have a postdoc called Michael Swart, and we're looking at combinations in general of monads with guarded recursion. And there are other ways of combining them. And that might be useful, I think, maybe for programming in this type theory. You can use it. You can view the denotational semantics. It's essentially a shallow embedding of this programming language into the metalanguage. So it's a way of programming with them. And I think maybe from the programming perspective, it might be interesting to do other combinations, and then it's not as generic as you say. But I would expect that these results could generalize, yes.
Thank you.
Are there other questions? No? So we can thank Rasmus again.